This lecture is on the exponential time hypothesis. So for some problems that we have seen, we have established algorithms, and usually we denoted running time with the O star notation. So let's say our brute force algorithm has running time O star of 2 to the power n, and then we're able to improve this to maybe O star of 1.5 to the power n. And then somebody else comes along and improves it to O star of 1.4 to the power n. And so there might be smaller and smaller improvements. Maybe the best known algorithm is something like 1.32 to the power n. But how far can this go? How much can we keep improving these running times? So the exponential time hypothesis and the strong exponential time hypothesis will allow us to establish lower bounds, saying that, well, you cannot really go below some certain level, otherwise you would enable a faster solving of some problems where we think that maybe they don't have faster algorithms. So this problem is the satisfiability problem. So we will review the satisfiability problem, case set, and then we'll briefly discuss sub-exponential time algorithms. We will see the exponential time hypothesis and the strong exponential time hypothesis, and then we will establish lower bounds based on these hypotheses. Okay, the satisfiability problem is the problem where we have as input a propositional formula in conjunctive normal form. As a parameter, we consider now the number of variables of this formula. And the question is whether there exists an assignment to the variables that satisfies all the clauses of the formula. And then, of course, case set is the restriction where every clause in the input has length at most k. So down here we have a 3-set formula because every clause has length at most 3. And if we set the green variables to true and the red variables to false, then we will satisfy this formula because the first clause is satisfied by x1, the second clause is satisfied actually by all the literals, for example, not x2. The third clause is satisfied by x1, and the last clause is satisfied by not x4. So what are the fastest known algorithms for the satisfiability problem? The brute force algorithm runs in time O star of 2 to the power n. So for every assignment to the variables, it checks whether this assignment satisfies the formula. Checking whether an assignment satisfies the formula can be done in linear time. And the number of assignments is 2 to the power n. Since for every one of the n variables, we have 2 possibilities, setting it to true or setting it to false. So what have people done to improve on this algorithm? Well, after more than 50 years of set solving, and there's a whole community that works on this problem. There's a set association, there's a conference on the satisfiability problem, there's a journal, and there's annual set competitions where people submit their solvers. The fastest known algorithm has running time O star of 2 to the power n times 1 minus 1 over order log m divided by n, where m is the number of clauses. And so if you look at this carefully, you'll notice that, well, this is not even O star of 2 minus epsilon to the power n. For the satisfiability problem, of course, our number of clauses could be exponential in the number of variables. But so the O star notation soaks up everything that's polynomial in the instance size. So everything that's polynomial in the number of clauses as well. So this running time is not even 1.9999 to the power n. So just as a little bit of a spoiler, the strong exponential time hypothesis will suppose that there's no algorithm for the satisfiability problem with this kind of running time. So there's no algorithm which solves the satisfiability problem in time 2 minus epsilon to the power n for any epsilon that's greater than 0. And for restrictions such as the phi satisfiability, or actually the k satisfiability for any constant k, we do have faster algorithms. For phi satisfiability, the fastest one are 1.3280 to the power n time algorithm. That's deterministic. And if we allow randomization, the fastest one is a 1.3070 to the power n time algorithm. So could it be that phi set cannot be solved in sub-exponential time? So here the 2 to the power small O of n running time is, well, 2 to the power of something that's that grows strictly slower than any linear function. So for example, could it be that phi set cannot be solved in time 2 to the power square root of n, or 2 to the power square root of n times log n. And so this will be the basis for the exponential time hypothesis. And the second question is, could it be that SET cannot be solved faster than 2 to the power n? So could it be that SET cannot be solved in time 2 minus epsilon to the power n for any epsilon that's greater than 0? And this will be the basis of the strong exponential time hypothesis. So we're talking about possible sub-exponential time algorithms for the phi satisfiability problem. But does that make sense at all? So are there NP-hard problems that can be solved in sub-exponential time? The answer is yes. For example, the independent set problem remains NP-complete even when the input graph is planar. So, and the graph is planar if we can draw it on the slide with no crossing edges. So now if I want to add another edge, I have to go around. So an example of a graph that's not planar is a complete graph on 5 vertices. I could go around here, I could go around here, but now if I want to add this edge, I'm in trouble. So independent set remains NP-complete for planar graphs, but planar graphs have trivials order square root of n. And if we think about planar graphs that have really large trivials, so one example is grids. So let's say we have the same number of rows as columns. Our tree decomposition for a grid would basically choose one dimension, either the columns or the rows, and then let's say we choose the columns. So the bags of our tree decomposition would basically be columns, but then to move from one column to the next, we have to find a way to cover all the edges in between. Right, so this could be one bag of our tree decomposition, and then so maybe our next bag contains, well, the top vertex of the next column as well. And then we can basically forget this vertex because, well, we have handled already, if we move from left to right, we have already handled all the edges that are incident to this vertex. So now our next bag would look like this. And then we would also add the second vertex of this column, and then we can forget about this vertex. So then our next bag would be the same bag, but this vertex removed, etc. So in this way we can walk along this grid, and every bag will have trivials order square root of n. Then for planar graphs in general, this can also be done, and this is by the planar separator theorem of Lipton and Tarjan. Okay, so we can find tree decompositions of width order square root of n for planar graphs, and we already know a tree decomposition based algorithm for independent set. So we can conclude that independent set can be solved in time 2 to the power order square root of n. And this is a sub-exponential time algorithm for this NP-complete problem, independent set on planar graphs. Okay, so for some problems we will want to rule out sub-exponential time algorithms, and for other ones we will want to find a more fine-grained lower bound. Like we could say maybe that you cannot do better than 2 to the power n half, unless you can also find a faster algorithm for satisfiability. And we will do this using reductions. First, let us formally define the exponential time hypothesis and the strong exponential time hypothesis. The first thing to do is to define this variable delta k for every k at least 3. So delta k is the infinimum of the set of constants c such that k set can be solved in time O star of 2 to the power c times n. And so why do we take the infinimum here instead of the minimum? Well, the infinimum is much nicer for an infinite set. So the infinimum of a set of numbers is the largest number that is smaller or equal to each number in the set. For example, the infinimum of all the numbers that are greater than 0 is 0. So for infinite sets, we will usually use the infinimum, because the minimum doesn't make sense. So if we take the minimum of the set here, of all the numbers that are greater than 0, then, well, for every number that we could try, we can always find a smaller one. And then this set doesn't have a minimum, and that's why we use the infinimum instead. Okay, so the exponential time hypothesis is a conjecture, so it's not proven, of course, that assumes that delta 3 is more than 0. So what that means is that, well, so there is some constant, delta 3, such that, well, the fastest known algorithm has running time at least delta 3 times n. O star of delta 3, 2 to the power delta 3 times n. And this is more than 0. So meaning that we do need exponential time to solve 3 satisfiability. Okay, and then the strong exponential time hypothesis assumes that, well, as k becomes larger and larger, so as the clauses become longer and longer, the limit of delta k, when k tends to infinity, is equal to 1. So meaning that, well, for satisfiability, where we do have the possibly very large clauses, well, the running time will be at least 2 to the power n. So the exponential time hypothesis implies that 3set cannot be solved in sub-exponential time, and the strong exponential time hypothesis implies that set cannot be solved in time O star of 2 minus epsilon to the power n for any positive epsilon. Okay, so now we want to use these hypotheses and use reductions to basically establish lower bounds for other problems as well. So these are now the lower bounds for 3set and for set, and we will investigate what other lower bounds does it imply. and for this we need reductions. So we will suppose that the exponential time hypothesis is true, and we want to infer lower bounds on the running time needed to solve other problems. And so I already mentioned that we will use reductions to do this. So suppose there's a polynomial time reduction from 3SET to some graph problem pi. And this reduction constructs an equivalent instance where the number of vertices of the output graph equals the number of variables of the input formula. So the vertex set, or the size of the vertex set, is equal to the number of variables of f. So using this reduction, we can now conclude that if the graph problem has a sub-exponential time algorithm, then 3 satisfiability also has a sub-exponential time algorithm. And this is just by using this reduction and the algorithm for the graph problem. And this would contradict ETH. Therefore, well, if we do have such a reduction, then we can conclude that the algorithm, the problem, has no sub-exponential time algorithm, unless, of course, the ETH fails. The issue with this approach is that many reductions from 3SET create a number of vertices, variables, or elements that are related to the number of clauses of the 3SET instance. So here we had that we wanted that so the number of vertices of our graph problem is equal to the number of variables of the 3SET formula. But many reductions would create some variables for or some vertices for the variables of the formula and some vertices for the clauses of the formula. And then we're in trouble because the number of clauses can be cubic in the number of variables. So it would be nice to have like a variant of ETH where we say that, okay, even if our 3SET formula has a linear number of clauses, then it can still not be solved in sub-exponential time. And that's where the sparsification lemma comes into play. So it says that, well, for each epsilon greater than 0, and so this epsilon will allow us to speak about these sub-exponential running times here. And each positive integer k, let's take k equals 3 because we are talking about 3SET mainly. So there is a sub-exponential time algorithm that takes as input a 3-cylinder formula with n variables, and it outputs an equivalent formula that is much larger, so it has actually sub-exponential size, and it is a big OR, so disjunction of a sub-exponential number of formulas fi, where every formula fi has the same variables as f, and each fi is sparse. So each fi has a linear number of clauses. So a number of clauses that's linear in the number of variables. Okay, so why is this important? So this is now a sub-exponential time algorithm that creates a disjunction of a sub-exponential number of formulas, and each of them is sparse. Okay, now if we had an algorithm, a sub-exponential time algorithm, to solve sparse formulas, then what we could do is, well, we could use this algorithm here. It runs in sub-exponential time. We could produce this big formula f prime, and then using our sub-exponential time algorithm for sparse formulas, we could solve each of these sparse formulas in sub-exponential time, and then return the result for the formula f prime. So this would then imply a sub-exponential time algorithm for 3SET. So this means that if the ETH is true, then 3SET cannot be solved even for sparse formulas in sub-exponential time. In other words, we can conclude that 3SET cannot be solved in time O star of 2 to the power of little o of n plus m, where n is the number of variables and m is the number of clauses of the formula. Okay, so now let's say that a and b are two parameterized problems, f and g are two non-decreasing functions, and suppose there exists a polynomial time reduction from a to b, and let's say the parameter of the instance of a is k, and the parameter of the constructed instance b is at most g of k. Then if we have an O star of 2 to the power of little o of f of k time algorithm for b, then this implies that we, by the reduction here, also get a O star of 2 to the power of little o of f of g of k time algorithm for a. So this of course just works by applying, if we want to solve a problem for a, an instance for a, then we just apply the reduction, use the algorithm for b, and return the result. So it seems that, the kind of reductions we should be looking for is, polynomial time reductions, such that the parameter of the constructed instance is at most some small function of k. Because, the small function here will somehow blow up the parameter here. Okay, but of course, as in parameterized reductions, maybe we can now relax this polynomial time condition here, because maybe we can allow it to take sub-exponential time. Mostly we will look at polynomial time reductions, but to give you the most general kind of reductions we could use, so here are the surf reductions. So a sub-exponential reduction family from a parameterized problem A to a parameterized problem B is a family of Turing reductions. So what is a Turing reduction? Well, it's a reduction which, it is an algorithm for A which makes queries to an oracle for B. And this oracle solves any instance for B in constant time. So our Turing reduction is just an algorithm for A that basically calls a solver for B. Okay, so we need to have such a Turing reduction for each epsilon greater than 0. And since we have such a reduction for each epsilon greater than 0, it's called a reduction family, such that for every instance I for A with parameter k, the running time is O star of 2 to the power epsilon times k. And for every query I prime to B with parameter k prime, we have that k prime is order k. So k prime is linear in k, and the size of I prime is polynomial in the size of I. So now, okay, so if B has a sub-exponential time algorithm, then of course every query to B can be replaced by a sub-exponential time running time, and the overall running time, excluding these oracle calls, is also sub-exponential. So in total we get a sub-exponential time algorithm for A. So if A is surf-reducible to B and A has no sub-exponential time algorithm, then we can conclude that B also doesn't have a sub-exponential time algorithm. Let's try and prove that vertex cover has no sub-exponential time algorithm. And for this we will reduce from 3set to vertex cover. And we will give a polynomial time reduction. Of course we could use surf reductions, but here we don't need the full power of surf reductions. A polynomial time reduction will be sufficient. For simplicity we will assume that all clauses have length exactly 3, Otherwise, we could, of course, add some dummy variables to make all clauses have length exactly 3. So let's say that this is our 3CNF formula. So we have 4 clauses, and let me show how the reduction works visually. Okay, so for every variable, we have 2 vertices. So one corresponding to the positive literal on this variable and one corresponding to the negative literal. And so we will reduce to vertex cover, and of course our assignment that we want to find will correspond somehow to a vertex cover. And we will not assign u to true and u to false at the same time. So that's why we are going to add an edge between u and not u. So selecting this vertex into our vertex cover will correspond to making this literal true, so making u true, and selecting this vertex into our vertex cover corresponds to making this literal true, so making not u true, so making u false. Okay, so we have such an edge for every variable in our formula, and now for every clause we also have 3 vertices. So we will have a triangle for each clause. So let's look at the first clause. We have u, v, and not y. So we will have one vertex of the triangle that's adjacent to u, one that's adjacent to v, and one that's adjacent to not y. Okay, so and we keep doing this for every clause and for every variable, and this is our construction. So now, what is k? So we have to set k to some value. And we know that, well, we need at least one vertex in our vertex cover to cover every gadget corresponding to a variable. So for each variable gadget, we need at least one vertex to cover this edge. We also know that for each clause gadget, so for each of these triangles, we need 2 vertices in our vertex cover to cover these 3 edges. And that's it. So our budget for the vertex cover problem will be exactly, so the number of variables, so there's exactly this. So if n is the number of variables and m is the number of clauses, our budget will be n plus 2m. So we don't have any slack at all. So we know that we need at least this many vertices in our vertex cover, and we will not allow to add any more vertices into the vertex cover. So what this gives us is that, well, we know that for every triangle, from every triangle down here, we will select exactly 2 vertices into the vertex cover. And for every one of the variable gadgets, we will add exactly 1 vertex into the vertex cover. Okay, so now our assignment corresponds to, well, making the corresponding literal true. And so if this literal here, for example, is true, if u is true, then, well, this edge that goes from u into the triangle is covered by the vertex u. And, well, the other edges incident to the triangle are covered by the 2 vertices that we put into the vertex cover from this triangle. So since for every triangle we add exactly 2 vertices into the vertex cover, there's always exactly 1 vertex that's not added into the vertex cover. And that's why the edge, or any edge that goes from at least one, or from this literal that's not in the vertex cover, so this edge must be covered by the corresponding literal in the variable gadgets. And that literal will satisfy the clause. Okay, so if we're given the 3CNF formula with n variables and m clauses, we have created a vertex cover instance with how many vertices? Well, we have 2 vertices for every variable, and we have 3 vertices for every clause. So the number of vertices is 2n plus 3m. How many edges did we create? Well, for every variable, we added 1 edge. And for every clause, well, we added the 3 vertices inside the clause gadget. And for every literal in the clause, we had 1 outgoing edge into the variable gadgets. Okay, so the number of edges is n plus 6m. And we set k to be equal to n plus 2m. So we see now that if 3set has no 2 to the little of n plus m time algorithm, then actually vertex cover has no algorithm with running time 2 to the little o of the number of vertices. It has no algorithm with running time 2 to the little o of the number of edges. And it has no algorithm with running time 2 to the little o of k. Because all of these are linear in n plus m. So we get these 3 results from this one reduction. Okay, let's also try and use the strong exponential time hypothesis. And so we see that what we did here, so here it was sufficient that the parameter of the resulting instance was linear in the parameter of the input instance. So here we had the 3set had parameter n plus m. And it was sufficient that the output instance, so vertex cover, had, well, the parameters that we were interested in needed to be linear in the input parameter. But for the strong ETH hypothesis, we need to be even more fine-grained. So now we actually care about the constants in these linear relationships. And we are going to try and establish a lower bound for hitting set. So what is hitting set? Well, as input we have a set system, so a set of elements, and then also sets of these elements, and an integer k. And the question is whether we can find k elements such that each of the sets contains at least one of those selected elements. And the parameter we're interested in is the number of elements. Okay, we will give a reduction from satisfiability to hitting set. So although this is a 3-CNF formula, our reduction needs to work for arbitrary satisfiability instances. And so I'll describe the incidence graph of the equivalent hitting set instance. So in the incidence graph, we of course have elements on one side and sets on the other side. And an element is adjacent to a set if the element occurs in the set. So we have 2 elements for every variable, and these 2 elements correspond to both literals of this variable. And we will set it up such that a hitting set corresponds to an assignment. So we will want to select elements that correspond to an assignment. So for every variable, we want to select either the positive literal or the negative literal. Okay, so if we have a positive and negative literal of a variable, we will want to add a set that contains both of them. And then our hitting set will select at least one of them. But now we will set the budget such that we can select k elements, and k corresponds exactly to the number of variables of the CNF formula. So meaning that for every variable, we will select exactly one literal. And then this will correspond to an assignment. Okay, so now we want this assignment to be satisfying. And that's why for every clause, we will add a set. And this set contains exactly the literals that occur in this clause. So for the first clause here, we will add a set that contains the elements u, v, and not y. And you can see now that, well, if this clause is satisfied, then we have exactly one, or at least one positive literal in, at least one literal that's set to 1 in the assignment, meaning that we have at least one element that hits this set that we added. Okay, and you can see in this way that a satisfying assignment for the formula corresponds to a hitting set of this instance and vice versa. Okay, so now for a CNF formula with n variables and m clauses, we have created a hitting set instance whose number of elements is twice the number of variables of the CNF formula, and k, the size of the hitting set that we need to find, is equal to the number of variables of the formula. So which parameter were we interested in? So it was n, the number of variables, the number of elements. So the number of elements of the hitting set instance is 2n. Okay, so now let's say that we can use this reduction to solve the satisfiability problem. So if we have a satisfiability instance, so we have a formula f, it's a set formula, and here we have hitting set. Now our reduction in polynomial time, it takes a formula on n variables, it creates a hitting set instance with a number of elements that's 2n. Okay, so now if hitting set can be solved in time c to the power 2n, then set can be solved in time c to the power number of elements, b. So then satisfiability can be solved in time c to the 2n. So the strong exponential time hypothesis supposes that c to the power n is, well, this is at least 2 to the power n. So roughly. So c squared should be at least 2. So that's why we can conclude now that under the strong exponential time hypothesis, hitting set has no O star of 2 minus epsilon to the power number of elements divided by 2 time algorithm for any epsilon greater than 0. And of course, if c is less than square root of 2, then, well, we would violate the strong exponential time hypothesis. And of course, the square root of 2 is 2 to the power 1/2. With a more ingenious reduction, one can even show that hitting set has no 2 minus epsilon to the power number of elements time algorithm for any epsilon greater than 0 under the strong exponential time hypothesis. And this was proved by Sigan and others. You can read much more on the exponential time hypothesis and the strong exponential time hypothesis in these textbooks. And these are the references of this lecture.